In this video, we'll look at the first section of Chapter 5 on relationships between categorical and quantitative variables. We'll look at how to handle two or several sample designs, as well as paired designs. We'll look at displaying and summarizing these relationships. We'll talk about different notations that we use. We'll discuss the role of spreads and sample sizes in these comparisons. To give you a sense of where we are, among the four stages, we're now talking about displaying and summarizing data, but we have moved on to relationships between two variables, in this case, the relationships between a categorical and a quantitative variable. Recall that when we're looking at a single quantitative variable, we may choose one of these three things to display the data: a stem plot, a histogram, or a box plot. And we have two techniques for summarizing quantitative variables, using a 5-number summary or using the mean and the standard deviation. Now, when we're talking about a relationship between a categorical and a quantitative variable, we'll use the categorical variable as the explanatory variable and the quantitative variable as the response variable. The way that we display and summarize this relationship is simply an extension of the way that we display and summarize a single quantitative variable. When we're talking about a relationship between a categorical and a quantitative variable, we might be exploring a two-sample study, a several sample study, or a paired study. When we begin discussing inference later on in the term, the method and the procedure that we'll use will differ depending on which of these three situations we find ourselves in. We'll start with the two-sample. When we want to display and summarize the relationship between a categorical and a quantitative variable, where the study is designed as a two-sample study, we will frequently use side-by-side box plots. The way this works is, for each possible response to the categorical explanatory variable, we'll create a box plot for the quantitative variable for each of those possible values for the categorical variable. In order to make the comparison, we want to make sure that both are done on the same scale. These box plots will be done vertically, so the y-axis should be shared between the two box plots. To summarize a relationship, we want to either compare the 5-number summaries, which we can do visually by looking at the box plots, or compare the means and the standard deviations inside each group. Later on, when we talk about inference, we will focus on the standard deviation and the mean, not the 5-number summary. When we're looking at two-sample data, there are a couple of different ways that we can format it for display. If you look at the student survey data, you might see columns for male earnings and female earnings on one of the sheets. Is there a different way that we can format this data? Currently, we have the two categories at the top, male earnings and female earnings, and then the data values underneath. Another way that we could do it is report each data point as an earnings value, and then beside that, report the gender. So what you see is each data point becoming a value in the left-hand column, and then the gender is reported on the side in the second column. So for this set of earnings data, with gender as the explanatory variable and earnings as the response, we will display and summarize by looking at side-by-side box plots. Notice that the box plots are oriented vertically. On the horizontal axis, we have the possible values for gender, male and female. Also notice that both share the same vertical scale. That same vertical scale is crucially important if we want to do good comparisons. Now, What can we learn from looking just at these box plots? Well, first, the center for males is a little bit higher than it is for females. You can tell that by looking for the median line. Do you see it? Do you see that it's a little bit higher? We can also judge the spread. The spread in this case is indicated by the height of the box in the box plot. Notice that the height for the male box is just a little bit bigger than the height for the female box. Finally, we can look at the shape of each of these distributions, noticing that there are a ton of outliers indicated by the dots here. Both of these distributions are very sharply right skewed. To summarize, we'll want to compare the measures that we have for center, for spread, and for shape. A computer program has spit out the following summaries for this two-sample design. Females are the numbers at the top. Males are the numbers at the bottom. So by looking at this output, what can we learn? First, let's look at the centers. We have two measures for the center, the mean and the median. Note that for both, they're higher for the males. Next, we look at spreads. We have two measures for spreads, standard deviation and IQR. The standard deviation for males is higher, and the IQR for males, which is 3, is bigger than the IQR for females, which is 2. Finally, we can get a little bit of a sense of the shape of each distribution by noticing that the maximum value for both are far, far higher than Q3, which means that we're definitely going to have high outliers for both. Noticing also that the mean for both is above the median, we have strong evidence to suggest that the data are skewed to the right. Now that we've looked at two sample studies, let's consider several sample studies. Here's an example. Math SAT scores are compared for samples of students in 5 class categories: first year, second year, third year, fourth year, and other, which generally indicates 5th or higher. What can we tell by looking at these box plots? Well, looking at the centers of each box, it seems that our measure of center is going steadily downward. So, as the year goes up, SAT average goes down. Can you think of a reason why that might be? If you know that the samples all come from students taking an Intro to Stats class, why do you suspect they would go down over time? There are a couple of confounding variables I can think of. See if you can think of any. So, several sample studies are simply an extension of two sample studies. Instead of 2 possible values for the explanatory categorical variable, we'll have more than 2. Now let's look at paired designs. When we have a paired design, we will typically look at a histogram of the differences to display the data, and we'll report the mean and the standard deviation of the distant differences to summarize the data. Let's look at an example. In the student survey data, we see numbers for age of mothers and age of fathers. We can compare the ages to see if mothers or fathers tend to be older. Questions we might ask: why is this design paired and not 2 sample? How will we display and summarize the relationship between parent sex and parent age? And finally, what results would you expect to see? Do you think mothers in general are older or fathers? This is a paired design because for every student we have 2 numbers, mother's age and father's age. Because this is a paired design, we'll use a histogram of age differences to display the data. And to summarize, we'll look at the mean and the standard deviation of those differences. Personally, I suspect that we'll see that fathers tend to be older than mothers. So, considering mother's age and father's age from our sample, here's a histogram of the differences, father's age minus mother's age. It's important to report in which direction you did the subtraction. In this case, father's age minus mother's age mean that positive numbers, that is from 0 and to the right, indicate fathers being older than mothers because father's age minus mother's age is positive. Whereas numbers that are negative to the left of 0 indicate that the father is younger than the mother. Now, what can we learn from this histogram? Well, notice that the center, that is approximately where we see the peak, is at maybe 2 or 3, but it's positive. And remember, positive numbers indicate fathers are older than mothers. Next, looking at the spread, we can see that most of these differences are within 2 to 3 years of the mean. So if we peg the mean at this tallest bar, and we go up and down by a couple of years, sure enough, that covers most of the data. Finally, we can see that the distribution is skewed to the right. The tail over here is stronger than the tail to the left. So that means that some of the fathers are much older than the corresponding mothers. Let's take a look at Excel to see how we can get those histogram and as well as the mean and the standard deviation of the differences that we're interested in. So here's the student survey data. I'm going to scroll over to the data that we have for mom's age and dad's age. I'm going to copy those out of the spreadsheet and paste them into a new sheet. Now you might notice that some of the data points, like the very first one here, are missing part of our data. We need to toss those out. So I think the best way to get those is to select them both and sort. So I'm going to select both columns. Under data, I'm going to go to sort. I want to make sure my data has headers is checked. And I want to sort by mom's age, smallest to largest. What this will do is it'll put all the blank mom's ages at the very bottom, and I don't see any. But as we scroll through, you might have seen several blank dad's ages. So let's go back to sort again. And this time, let's sort by dad age, smallest to largest. Now when we scroll down to the very, very bottom, you'll see all the blank dad's ages down here at the end. So what I'm going to do is take all the corresponding mom's ages, and I'm going to delete them right out by selecting them and pushing the delete key. Now we've got all of our lovely paired points, mom's age and dad's age. So since this is paired, remember what we want is the differences. As before, I'll do dad's age minus mom's age. Now we could go through and do all these subtractions by hand, but there are over 400 of them and that would take forever. So let's do this with a formula. Since this is an Excel formula, I'm going to start by pushing the equal sign. That tells Excel that it's about to do a calculation. And what I want to do is dad's age minus mom's age on the same row. So I'll click on the dad's age that I want, and then I'll push the minus key, and then I'll click on the mom's age that I want, and I hit enter. So you can see that Excel has correctly computed that difference. Now to do all of these at once, I'm going to hover over the bottom right corner so that my cursor changes to that little black plus sign. I'm going to click and drag all the way down to the bottom of our data. and all the differences are filled in. Now to get the, let's say, the mean and the standard deviation, I'll come over to the side, mean of differences, and I'll type equals. Remember the formula for mean is average, and I want the average of everything in column D. The average function, if it sees a number that is, or an entry that's a word, like differences or blank, it'll just ignore them. So we get an average of 2.44. Now the standard deviation of the differences. Oh, remember there are a couple of different standard deviations. So instead of starting with the equal sign, I'm going to go to the formulas box. I'm going to go to more functions, statistical. Remind myself there are two standard deviations. This is a sample, so I'm going to go to standard deviation S. So standard deviation of samples, I'm going to click on the box. I'm going to select differences, the differences column. I'll expand that back out and hit OK. So the standard deviation of the differences is a little bit bigger than 3. What about the histogram? Well, remember in Excel, to get a histogram, we want to go to Data and Data Analysis. You may recall that we have to put in the Analysis Toolkit under the Options. We did that in a previous video. So I'm going to click on Data Analysis, and I want a histogram, so I'm going to select histogram. Oh, remember for histograms we need bins. So before we do this, let's cancel. In order to figure out what our bins need to be, we need to know our maximum value for differences and our minimum value for differences. The best way to do that, but there are formulas, maximum and minimum, that'll tell you. But I'm going to do it by sorting. So let's sort differences, smallest to largest. And that didn't work. What happened? Sort differences on values, smallest to largest. That is not what's happening. It seems to be sorting on Dad's age. Let's select all 3 of these, and let's sort by differences, smallest to largest. There. For some reason, that did it. Okay, so I see the smallest difference is -9. And let's do the same sort. Whoops. I need to select again. Let's select everything. So let's sort again, largest to smallest. That saves us from having to scroll all the way down to the bottom. The maximum is 27. So -9 to 27 means maybe we want to go -10 to 30, and maybe we'll count by 2s. So let's get our bins. Let's do -10, and then my next bin is going to be equal to 2 plus the previous bin. And I need to go all the way up to 28. That'll be the biggest one we need since our maximum was 27. Okay, so now let's go to Data Analysis. I'll select histogram. The input range is in column D, and the bin range is in column F, but not the whole thing. I'm just going to select it. The data has labels, so I'm going to check labels. I want the output to go over here to the side of the bins, let's say. And I want a chart, so let's choose chart output and click OK. So there we see our bins and the frequencies. Notice there are a couple of these we don't need because the frequencies are 0. There's nothing below -10. So I'm going to delete that by selecting the 2 points. I'm going to right click on it, click on delete, and I'm going to tell it to shift cells up. I'm going to click OK. Notice that changed the histogram because it got rid of that -10 bar. and it split all this stuff up. I also don't need the more down here on the end, so I'm going to delete that out. Delete, and I'm going to shift cells up. Now, some of these other zeros I don't want to delete because they represent space in between data points. So let's make this histogram a little bigger so we can see it better. I can maybe move it over some. Whoops, I didn't mean to do that. I clicked the wrong place. Let me click here and move it over some. You may remember the trick we did before to make the bars wider. Oh, I'm not doing that right at all. Here we go. I'm going to click. No? Come on. Let me move this back over. I'm going to click this handle here and make this picture taller. And now I'm going to move the whole chart over a little bit. I'm going to right click on one of the bars and I'm going to format data series, and I'm going to turn that gap width way down so that the bars look like they're closer together. I think that's a lovely histogram for our data, and it looks very much like the one that we just saw in the slide. Now let's talk about notation. For a two-sample or several sample design, we'll use the same notation that we've used for means and standard deviations, except we'll attach subscript numbers. 1 and 2 for a two-sample design. We'll include 3 and 4 with the 1 and the 2 if it's a four-sample design, and so forth. For a paired design, we'll use just the single mean and standard deviation, but we'll attach a subscript D to indicate that it's talking about differences. For example, for a sample of countries, we consider the illiteracy rates that are recorded for each gender group. So countries are the individuals, and we're looking at illiteracy rates for each gender group within each country. So how do we denote the mean of the illiteracy differences? We're using differences because this is a paired study for the sampled countries. And how do we denote the standard deviation of the illiteracy differences for these sampled countries? Well, because it's a paired design, we'll use the same notation that we usually use. For the mean, we'll either use X bar with a subscript D or mu with a subscript D. Because we're using a sample, we'll use X bar subscript D. We'll usually read that as X bar sub D. The standard deviation then, again since it's a sample, we'll use S for standard deviation and a subscript D to indicate that it is for differences. Another example. Here, records are kept concerning percentages of schools at all private, state, and state-related schools receiving Pell Grants. How do we denote the mean percentages for each of the three types of school and the standard deviations of percentages for these three types of school? Well, the mean percentages for the three types of school, because there are three of them, we'll use, this is not a paired design, this is a three-sample study. We'll use the typical notation with subscripts 1, 2, and 3. Since the background information tells us we're looking at all schools, we know this is a population. So we'll use mu. Mu sub 1, mu sub 2, and mu sub 3 to indicate the mean at private, state, and state-related schools, respectively. Similarly, the standard deviations will be indicated with sigmas with subscript 1, 2, and 3. Now, let's talk about relating sample and population differences. If we have several different groups, when we are asked if the responses are different somehow, what do we mean by that? Well, the first thing we want to compare if we're looking for a difference between two groups or more groups is to look at the center, the means or the medians. Differences will be stronger if the spreads are smaller. In other words, there could be a pretty reasonably large difference between, let's say, the medians of two groups, but if the spreads are also enormous, then that difference is not as strong. Even a tiny difference in the means can be considered a strong difference if the spreads are sufficiently small as well. We'll say more about this over the next few slides. One thing that will affect the strength of the differences that we observed is the sample sizes. The bigger the sample is, the stronger the difference is that we can infer. Again, I'm talking about inferring something, so we're talking in a way about inference. When we want to infer something about means, we'll consider all three of these different measures for the variables. They're all important. But next, let's focus on the spreads. Let's look at an example of the impact of spreads on how we perceive the difference between two means. Consider this scenario. An experiment compared test scores for gum chewers and non-gum chewers who were studying anatomy. The means on the tests were 83.6 for the chewers and 78.8 for the non-chewers. Here are the side-by-side box plots that might have resulted from our data. Remember, in some box plots, such as these, the means are indicated with the dots inside the boxes. So each of these indicates a mean for 83.6 for the gum chewers and 78.8 for the non-gum chewers. Which of these two scenarios, the one on the left with more spread or the one on the right with less, gives you more evidence that chewing gum is an aid to learning? The one on the right does. Because there's less spread, we feel that the means have a bigger difference. One thing that I look at in particular is, notice that the mean for the group on the left, the gum chewers, would be in maybe the 90th or 95th percentile of the scores for the non-gum chewers. Do you see how it's far above Q3 and it's close to the maximum value? Similarly, the mean test score for this one among the non-gum chewers would be below the 25th percentile for the gum chewers and is close to the minimum value. That is really, really convincing evidence. Now, one of these represents the actual data. If you think about the result that we're shown here, which one do you think is the actual data? In other words, if you had to guess, how strong do you think this relationship is? As I hope you guessed, the actual results are shown in the one on the left. The difference in means isn't strong enough to be able to conclude a relationship. Later on in the term, we'll look more closely at how to put a number on the strength of this relationship. But for now, this is good enough. Now, what about sample size? If we have the same scenario with gum chewers and non-gum chewers taking an exam, which would be more convincing to you that chewing gum is an aid to learning? If the sample size was 56 or 560? Well, remember that in general, the bigger the sample size, the better the results, as long as the study design is good. So, in our situation, would you be concerned about the experimenter effect, the placebo effect, a problem with the realism, about ethical concerns? Do you have non-compliance concerns? The most worrisome thing here is the possibility of the results being skewed by the placebo effect. Remember, there's no way to make this blind to the subjects. If I also told you, and this is true, this study was done by Wrigley Chewing Gum, I think you might also worry a little bit about the experimenter effect, since Wrigley would benefit if it could be conclusively shown that chewing gum did in fact aid studying. To wrap up, we've looked at, within two or several sample designs, how to format the display, either one column for each group or one column for each of the two variables. We talked about displaying them using side-by-side box plots and comparing the means and the standard deviations or the 5-number summaries so that we can compare the center and the spread. For a paired design, we looked at constructing a histogram of differences, and finding the mean and the standard deviation of differences. We looked at the notation, which, remember, depended on the design. If it's a 2 or several sample design, we'll use subscript numerals, 1 through however many samples we have. For a paired design, we use a subscript D. And remember that we'll use different notation for the mean and for the standard deviation, depending on whether we have a sample or a population. We also looked at exploring differences between sample means and the strength of those differences. And we saw how they could be affected by the spreads of our samples and by the sizes of our samples.